Oh, there, okay. I have put your slides in here too.
Thank you.
Can everybody online hear us? Somebody?
Yes.
Yes, very good. Thank you very much. Okay. Welcome everyone to this talk with myself and Patrick Hammer. That's called From Machine Learning to Machine Psychology. And we are very happy to be here at Digital Futures. Somebody asked here about the Stockholm AGI lab logotype down there. And this is really myself, Patrick, and Tony. Tony is also here in the audience today. And our research group, we really work with the implementation OpenRs for applications that Patrick and Tony has written, and we are so extremely grateful also to be funded by Digital Futures. Since Patrick is leaving with a flight, he will actually start talking about our latest development in NARS research. Please go ahead.
Thank you, Robert, for the intro. And as many of you know, Robert has been my postdoc advisor, and we have been looking at this experiential learning problems together, which I will now show to you. And especially with Tony Loftus, we have worked a lot to make this approachable. And what do we really want to do here? And that's the big question, of course. And we have multiple answers. One is, for instance, we see intelligence in natural species, in nature, basically. Different species which are able to learn hypotheses while they carry out tasks. And here, for instance, you see even a bumblebee on the screen, which is able to learn a quite complex task, which is to roll something into a hole in order to get honey. That's a quite advanced capability, which most people would not have expected that these animals are capable of. And of course, with ravens, and the situation is a bit different. Most people know that ravens have quite advanced capabilities and are considered to be more intelligent. But we want to be able to replicate this in addition to human level abilities. We also want to be able to replicate what animals can do. And for this, there's the central question: what is intelligence about? And for instance, here we see that we put this animal species into situations they have not particularly evolved for, yet they are able to adapt to these situations and carry out the task. So it has to be something which has to do with adaptation. And we can actually test for these abilities by putting systems into concrete situations where they have to learn something new and carry out a particular task. So this brings us to a working definition of intelligence, which is that we want systems which adapt under insufficient knowledge and resource. Or these insect brains you have seen, they are quite limited. There's only a certain amount of neurons in their head, and yet they can do certain information processing. Most of the information processing this species do is, of course, mostly concerned about the survival. And so it's highly tuned by the evolutionary process. But if we want to build intelligent systems, we essentially want systems which can also adapt to the environment and hopefully do so very effectively under the resource constraints under which the systems operate under. And the particular approach we have taken is a non-axiomatic reasoning system, which is essentially a reasoning system-based approach to intelligence, where we take logical reasoning and we build a system which can operate under finite processing demands, and we open new information at random, learn hypotheses, test them at random, and essentially acquire skills and knowledge while the system is operating. One of the challenges involved here is, of course, how to pick represent the knowledge in the system and so on. Many of these questions I cannot dive into the detail here because there's not enough time, but I can at least show you the basic knowledge representation which the system has internally. For instance, it is able to, it uses something called non-axiomatic logic, and this provides both the knowledge representation formats, like how different kinds of knowledge are represented within the system. For instance, inheritance statement, learning that cats are animals, or that Garfield is a specific kind of a cat, and that Garfield is also an animal. So it can express this kind of class hierarchy or taxonomy, this kind of relationships, but it can also represent causal relationships, which are really important if we want to build agents which actually carry out tasks in the environment to accomplish goals. So for instance, our system can learn that lightning leads to thunder, assuming that it can somehow observe lightning and thunder. So you give it this like multimodal experience where maybe it can observe the lightning strike visually, and maybe it has a sound sensor which allows it to detect thunder sounds. Then it will already, over the passing of time, when this events occur, will already build this hypothesis essentially. And here there's a key difference here to classical reasoning systems right here, which is the statistical dependencies essentially in some way. This is not just about whether lightning always leads to thunder. It's about relationships which most of the time hold, but maybe not always. Ravens are not always black. Maybe one is albino, has some genetic defect, and is born as a white raven, for instance. So most of this common sense knowledge which we use as humans in everyday life is actually not always true. Yet we use it because it's a very good description for most of the cases we encounter. So that's very important for the system to cover that. And in order to cover that, we have evidence values. We essentially, for each of these hypotheses, we keep track of how well they predict. For instance, if we look at lightning leads to thunder, okay, now lightning happens. Will thunder occur or will it not occur? If it occurs, it's positive evidence for the hypothesis. If it does not occur, it's negative evidence. So this is one of the key principles here. And we have built an implementation of the system which particularly uses these principles which I have just described to you and allows for real-time learning, essentially like we want the system to do. And essentially learn causal relationships from observations and then invoke actions which lead to the goals the system wants to achieve. So that's essentially the central part here. There's also some brief architectural overview which you can see here. Essentially we have some kind of attentional buffer, the green thing in the middle. That's like the central piece in the system. And from the left you see the green block. The green block essentially just says there are observations which come into the system from different sensors, and they end up into the attentional buffer of the system. And then you see the concept memory block, which keeps track of the long-term evidence of the events, like how often is it that ravens are observed to be black, for instance, essentially accumulating evidence over time. And then you can have this accumulated evidence, but also the evidence from new events which compete in the attention buffer. Essentially, the system can then do multiple things. It can construct hypotheses between events by selecting elements from this attention buffer, but it can also use these causal links you have seen, like lightning leads to thunder, to go backwards in order to derive subcores to invoke decisions which most likely lead to the consequences it has learned to happen when the conditions are met. So that's like a high-level overview of the system. And we see here that particularly with this animal model which we have developed, we particularly concentrated at sensory motor abilities, which is learning from event streams, learning this causal hypothesis, using them to achieve goals, and identifying the right events which are relevant to make decisions on. And I will give you a very concrete example very soon where you will see this ability. But before we go there, we look into some basic representations which the system can learn effectively. For instance, it can learn procedural hypothesis. If there's a door in front of me and I push it, it will be open, for instance. So it's like the temporal hypothesis with lightning and thunder, except that there's an operation involved as well, which the system can invoke whenever it wants to. It can use this push move whenever it wants, but it will not always have the same consequences. You push the wall, the wall will still be there. You push the door, it might open, dependent on the door. So it can learn this kind of procedural knowledge and can use this procedural knowledge and chain it together. So if you know you can get from A to B, and the system has also learned it can go from B to C, then it also knows it can go from A to C, for instance. So it can chain this procedural hypothesis together, essentially. And what's new in this particular system, we have also explored the ability to acquire relations of various forms. In the simplest form, it's relationships between observed stimuli. I could, for instance, say, this chair is smaller than this room. That's trivial. Or I could say this lamp appears brighter to me than this table. I could compare different things according to how bright they are or how big they are, and I could form these relations. Whatever you ask me, if one thing is bigger than the other, I will likely be able to answer. And we want the system to be able to do this as well. So we have multiple examples where we tried this capability and where humans can essentially compete against the system to get an idea of what this entails, what essentially this problem is about. In the simplest case, you see
the screen sharing is only for PowerPoint. Now you should see the screen.
Oh, wonderful. So here, for instance, you see different shapes. And the user in this case can either select the shape to the left or the shape to the right. But you don't yet know which one is the right shape. So you pick one and you get feedback. And it says, in this case, correct. But why was this the correct shape? Why was it? Was it because it was a rectangle? Okay, here's a rectangle. Oh, wrong. It's not because it was a rectangle. So I can now guess what is the criteria according to which I need to select either the left or the right thing. This criteria is not easy to find. Maybe I need always to select the rectangle because I tried. It failed. Maybe I need to select always the green thing. Maybe I need to select always the thing to the left. Maybe I need to select the thing which has the same color as the thing in the middle. And humans are very effective to figure this out, so maybe I will do. So let's try. So this I tried. This was a circle, but here we don't even have a circle. So essentially the task here is to figure out according to what criteria I should select the shape. Maybe if this one is red, I also need to select the red thing. Let's try. No, it's not. Maybe if this one is shaded, I need to select the thing with the same shade. Also not. Maybe what else could there be? I think I found it. The color? Which color?
I thought it was yellow.
No. No? I have not yet figured out, and interestingly, the system is already leading. It's already further in the process of figuring out what the right criteria is. And if I keep doing it, See, I might figure it out, I might not. I don't always figure it out actually.
What is this AGI then, I guess?
It has outsmarted its creator.
Yeah.
Let's try a bit. Any suggestions? I run out of ideas. Maybe the thing to the right? It's not the circle. I selected a circle. It's not a rectangle, so it cannot be about a particular shape. It can also not be about a particular color because there's green and green here. So what else can it be? Maybe if it's a rectangle on top, I need to select the thing to the left. I have no idea actually.
Maybe it's the position of the objects.
The position?
Yeah, because they differ sometimes. Sometimes it's touching the wall. Sometimes there's some gap.
This is a visualization issue. There's only 3 locations in this task: left, middle, and right.
Yeah.
This is one task, and the system is leading here. And if we rerun this, for instance, we can give the system a task. Pick always the thing which is brighter than the thing there in the middle. You can see the system essentially a fast forward of the system learning the right criteria. You can see after some time, but 75% correct after 100 steps. If we keep going here, you will see it will essentially get to higher percentages here. It's now even above 80% already. And we can also see, actually, it's a bit small text here, but it really takes the brightness relation between the thing in the middle and the thing to pick into account. That's one example, but we also have another one. PowerPoint. Here we have an example where the user needs to find the meaning of two letters. It could stand for brightness. It could stand for particular brightness values. It could stand for brighter or darker. It could stand for rectangle or triangle or circle. It could also stand for on the left or on the right. So we have to figure out the meaning. So I click, wrong, click, wrong. So Y is not about circle, maybe. Maybe it's also not about things on the right. Get it? Oh, this was Y now. Okay, so X, let's see. Maybe X is about circle? No? Maybe X is about the thing which is brighter? Yes, this seems to be the case. Now we have Y, so here I don't know what it really wants from me. But X, I have figured out, it's the thing which is brighter. Oops. And let's see if we can also find the meaning of Y. X is brighter. Y is darker. No. Yes, maybe. No. X is brighter. And Y is maybe. Maybe it's circle. So X is brighter and Y is circle. I think that's it. maybe not. Not sure what Y is, but I know what X is. So you see the problem here, how to figure out the meaning of the symbols. It's not that trivial, but humans can actually figure it out, like 100 real, and you will usually be very certain about what X corresponds to and what Y corresponds to. It's not a trivial task. It's a task where, surprisingly, the system was also not better in this case. Similar good, but it was only 28 clicks so far. So what's very interesting here is that this shows a very high-level hypothesis formation capability, where the system really learns to associate which relation to act on. Like, it really learns to what the symbols correspond to, essentially, and learns to make the decisions based on the right relationship between the perceivable objects. So this is just a demo to show you what this procedural learning can do. It's not the only thing we can do with that, but I hope it gave you some inspirations to be put into the system shoes to see the problems it's actually trying to solve. That's
Great.
Thanks
a lot, Patrick. Any 1 minute question for Patrick before he rushes to the airport?
Yeah. So other AI systems struggle with this specifically, right?
Mm-hmm.
Yeah.
That's true. Particularly the data efficiency is an issue because humans and animals, they learn really quickly. And this task is set up in a way that you have 100 clicks. Within the 100 clicks, you have to figure it out. There's just no other technique which can do that.
Yeah.
Which maybe has to do with the explicit hypothesis, representation, and ability to keep evidence for this different hypothesis. I think this is a very important principle here, which allows for this. Thank you, Robert, to give me the opportunity. Thank you. And see you soon.
Okay, so we will continue now. And how I organize this talk is in these topics. I will briefly say first something about artificial general intelligence. Then I will describe a particular approach to that is called learning psychology. I briefly say just a few words about NARS, the system that we use. And then I describe the combinations of these, learning psychology and NARS, that we call machine psychology. I provide examples of the research we have conducted, and also at the end touch on some application domains. And I think we might have a short coffee break in maybe 20 minutes or so. Okay. So artificial general intelligence. Who in the audience has not heard about artificial general intelligence? It seems like most people know about it. So this is really the task of creating a general purpose computer system, which is typically contrasted with these special purpose systems that are trained for a particular task, like image recognition or game playing or something. Margaret Bowden, who is a famous AI researcher, has labeled this the holy grail of AI research. And other people refer to this, for example, you, Henrik, in the audience, as the potentially most great invention of all time. So it's obviously a very, very influential thing if it can be built. But it's an extremely difficult task, of course, to build an AGI system. And even if, so to speak, the original goal of AI in the 50s was to create AGI, it's really since 2008, roughly, that there is a dedicated field within AI that is particularly about AGI, that has its own journal, community, conferences, and so on. And as I mentioned here previously, we had the 2023 conference in this building, for example. So since it is such an extremely complex problem, there are multiple approaches to the problem. And one approach that many people are fond of is that the brain should be simulated as close as possible. ChatGPT could be said to be a version of a path to AGI where we strive to mimic human behavior in conversation as closely as possible. So it doesn't have to do anything with brain states or something like that. NARS that we use is rather about identifying a single unifying principle. And as Patrick mentioned, in the case of NARS, that is the principle of adaptation with insufficient knowledge and resources. So that's another path or another way to build AGI that is not the same as GPT or not the same as HTM, for example. And me and my colleagues, we are really particularly fond of this animal way of using NARS that Patrick demonstrated, and I will show much more of that. Here is our colleague Chris Johansson, who is an AGI researcher from Iceland, and he was the editor of the latest proceedings on the AGI conference, and he wrote in the preface, "The biggest contribution to scientific knowledge that AI could provide is a comprehensive theory about intelligence. No real progress can be made without it." And I think that's a very good statement, and it summarizes a strong call from AGI researchers that this is not only engineering, there is a strong need for theory-driven research that can guide this. So then the question becomes how to find a good AGI theory. And what we have been exploring over the years is to take theories from the field of learning psychology, which I will explain more about now, to guide research in AGI. So, learning psychology, this is an excellent book about learning psychology that is freely available online from MIT Press, open access. It's written by Jan de Houwer to the right and Sean Hughes to the left. And they really emphasize the difference between functional and cognitive psychology. So they define learning as ontogenetic adaptation. So that's adaptation during the lifetime, so to speak. They define learning as that to start with. And then in functional learning psychology, they study what they call effects of regularities. So I guess all people have heard about the Pavlov's dogs and classical conditioning. So that's an example of regularities. So it's defined as an effect of stimulus pairings on behavior. So it's a regularity that food and the sound of the bell co-occur. That's a regularity. And we study the effect of that regularity on the change in salivation. So that's a really important point here, that the kind of domain we study here is really the impact of regularities on behavior. Another way to say it is that when does learning occur? That's really functional learning psychology. Cognitive learning psychology, on the other hand, is typically that we have some study of mental mechanisms that could explain the machinery of learning. So it could be association formation or some propositional network or some structure that we would assume would explain learning. And these are not like in opposition to each other. They are just very, very different. But functional learning psychology talk about when does learning take place, and mechanistic cognitive psychology try to understand what mechanisms make that learning happen. So just a few examples of learning, and I will describe it as from this functional learning perspective. So here we have a rat. So the rat has learned to do different behaviors, different music. So this is then an example of operant conditioning, because it's a change in behavior. If we talk about the learning history for this rat, the rat was not born with this ability. It has learned it during its lifetime. So to start with, it's an example of learning, how it learned to do this. It's an example of what we call ontogenetic adaptation. It's adaptive, and it has learned it during its lifetime. So it's a change in behavior, for example, an increase in correct responding, lever pressing, or turning around, because of the consequences. Because of the consequences, that has an effect on the increase in correct behavior, so to speak. And this music type can be said to further moderate this effect. So now, another way to just say it is that it's an impact of both music type and water on behavior change. So once again, this is an example of how we talk about learning as a function. The behavior change is a function of both music type and water, both the precondition and the consequences. The operant conditioning then can be described in this way, and this is actually how it was originally described by Skinner, as a functional effect rather than a mechanism. Skinner didn't talk about mechanisms. So it's perfectly possible to talk about this type of learning without using any particular mechanism like association or propositional network. What Jan de Houwer calls complex learning is one step up in complexity, and I will give 3 brief examples of that. So generalized identity matching or identity matching is simply to be shown a symbol, very similar to the experiment that Patrick showed, and we can train someone to, for example, pick the same symbol as on the top. And we learn that maybe for a particular set of symbols. But generalized identity matching to sample, that's really then to respond to this situation with symbols that you have never seen before. Then you have to act on the relation between events, so to speak. So given the history of learning identity matching with these symbols, I could predict, for example, that I need to act on the relation between the top symbol and the right symbol to pick the same. And here is an example of a sea lion that can learn to, for example, when palm tree is the sample, it picks the palm tree, but then with new symbols later, it can pick a symbol that it has never seen before because it is the same as in the middle. So how we express this in functional learning psychology is that the relation between two events can function as a particular cue of choosing left, for example. So Jan de Hauer called this an effect of meta-regularities. There are regularities of regularities. Some pattern that two events are similar, that can in itself be part of a pattern in that, if that occurs, I should do that, that leads to that consequence. So this is an example of complex learning that we still don't need any particular structure to talk about.
One quick question. You said that animals can do this as well, right? So
yes.
With the seal example, they can sort of transfer that that pattern, so to speak, that you should choose something similar. Okay.
Yeah. So it's not that all animals can do it, but for example, sea lions, rats, dogs can do it. And this is another example, also related to what Patrick showed, that we can imagine a task like this, that if all objects in the top matrix are similar, then I should choose this matrix with only similar objects. But if the matrix on the top are different objects, then I should choose those who are different. And here is a monkey doing that task. What happened to the monkey? The monkey disappeared. Anyway, it was here. Strange. It needs to touch the top one to get the bottom ones. So this is another example then of what animals can do. And here's another one that we can, out of two objects, be trained to pick the largest circle. But it's a non-trivial problem how to then generalize that to new shapes that I might never have seen before. So here is a dog doing that. So it has been trained on these circles, and you can see how quick it is to always pick the largest circle with a lot of different sizes. But now it sees stars for the first time. And you can see how it's a bit cautious before it picks the largest star, but that was correct. So it got, here's another dog. So all of these examples are, you could call it animal level intelligence, even if these are impressive behaviors. How can functional learning psychology then talk about human level intelligence? And here is a real groundbreaking part of learning psychology that occurred about 40 years ago. The paper that was published here in 2021 by Stephen Hayes and co-author says, the title is Relating is an Operant. A fly over 35 years of RFT research. RFT stands for Relational Frame Theory. But these 4 words capture so much that is of so much importance also for AI research. Relating is an operant, meaning relating in itself is a learned behavior. All these examples that we saw here was instances of operant conditioning. The rat with the music type and the monkey and the dog and the sea lion. Different advanced levels of operant conditionings. But can we learn the relating in itself in a way that it's not particularly tied to the situation in front of us? Can we learn that relating in itself as an operant? That was the brilliant insight by Stephen Hayes in 1982, that relating in itself can be learned. So what would that mean, that relating in itself would be learned? This would be the absolutely most simplest example, that if we assume that these are totally arbitrary symbols, and you need to pick left or right, and you pick that thing, and you get the feedback correct. Wow. Okay, how would you then do in this situation? Would you pick left or right? Martin?
Maybe
I would do that too. I would also pick left, because people with language ability, like immediately, oh, if A1 was the sample and I picked B1, oh, then it's probably I could reverse it if I know nothing else. So if B1 is the sample, I should pick A1. So this very, very simple behavior, so to speak, that 16-month-old babies can do. There's basically no other animal that can do this reliably. The sea lions have had some success, some pigeons under very specific circumstances, but generally it's quite fair to say that this is the simplest behavior that is human level intelligence, human level only intelligence. But how do we do this? People have thought about this for many times, but what relational frame theory suggests is that to be able to, I showed you this part, that if I learn to pick B1 in the context of A1, and maybe pick B2 in the context of A2, the bottom left corner here, then I could then, as we showed, probably turn this around and choosing A1 in the context of B1 and choosing A2 in the context of B2. But how did that happen? What learning history enabled that? How was that relating learned as an operant? And here's how relational frame theory suggests that it works. That in the top row, let's say that I learn it with feedback both ways. So in the context of X1, I'm trained to pick Y1. But also in the other way around, in the context of Y1, I'm trained to pick X1. So I have seen with feedback the pattern in both ways. So I, in some way, generate some, I see a more abstract pattern of switching positions. So it's the pattern of switching positions that is learned. and then can be applied in the bottom situation. That's the theory of relational frame theory suggests that how it works. This would be the most simple example then of learning a relation, a symmetrical relation. So relational frame theory then is, as I said, relating is an operand. This type of relating could be learned rather than built in, for example. So it is one way of talk about something like transfer learning. Learn a pattern of relating in one context, apply it in another. And as I said, human babies do this already at 16 months of age. And relational frame theory talk about a general pattern called arbitrarily applicable relational responding, AARR. That is really learning these very, let's call it abstract types of relating that is controlled by social cues rather than seeing, for example, the relation perceptually, like in all other animal examples. So the idea of intelligence in itself, from the perspective of relational frame theory, is simply complex combinations of various types of abstract relating. So AARR is a very general concept that is what we talk about in RFT rather than intelligence. So one can also say that intelligence involves a lot of learned behavior from the perspective of RFT. But the magic thing about this from the perspective of AI is that if a machine can learn to do AARR, oh my God, then it could really learn a lot of intelligent stuff during its lifetime, rather than having it built in from the start, so to speak. So it seems to be an extremely potentially important process for AGI research. I would go as far to say that maybe what we mean with general intelligence is arbitrarily applicable relational responding. So the question then is, can relational frame theory be the AGI theory that, for example, Chris Torrison was talking about, that is very, very strongly needed? So before answering that, what qualifies as a good AGI theory? What requirements do we put on a theory of AGI? So here is one suggestion from AGI researcher Pei Wang. He suggests that the theory of AGI needs to be correct, compact, and concrete. So relational frame theory is correct in the sense that there's hundreds of experimental studies, like validating it and showing it in lots of various situations. RFT and functional learning psychology is extremely compact. A very limited set of terms explain a lot. And however, RFT is not concrete in the sense that we can go directly from there to implementation. It's not possible to take this psychological theory, even if it's, so to speak, very formally described. We can't immediately just start implementing it in a computer. That's a problem with RFT. So how to make RFT concrete then? Well, that's where NARS comes in. Maybe we can use NARS to implement the principles from functional learning psychology and RFT. So to start with, there's a deep compatibility here. Learning psychology talks about learning as ontogenetic adaptation. And Pei Wang defines intelligence, his working definition that the whole system is based on, as adaptation with insufficient knowledge and resources. Okay, so they talk about the same thing at the core. And NARS is a principal AI in the sense that it seeks to implement a single principle. So in a way, this matches perfectly with functional learning psychology that really talks about learning principles. So the goal then of our research is to take relational frame theory and functional learning psychology and implement its processes using the non-axiomatic reasoning system. So that in itself is a bit weird, so to speak, to take a reasoning system which is typically associated with higher order abstract thinking. But we take a reasoning system to implement these basic biological learning processes. But as Patrick demonstrated, that works extremely well to reproduce this animal level behavior. So before we take a brief break, I will just say something again about NARS. And it is created by Pei Wang, who was a scholar in resident here at Digital Futures 2 times, 3 months in 2022 and 1.5 months in 2023. He was also Patrick's PhD advisor. And he has created this system, NARS, non-axiomatic reasoning system, that implements this non-axiomatic logic. So the thing that is stressed so much in this system is that it is based on the assumption of, it really is based on the assumption of insufficient knowledge and resources. And Pei's idea, like in the 90s or maybe 80s, was that he used a quite unusual logic, a term logic, to be able to fulfill that assumption of insufficient knowledge and resources. And extremely briefly, also as Patrick touched on, the system at each cycle applies logic rules over and over. The rules that are applicable are applied at each cycle in constant time. So the time complexity, so to speak, in each step is in constant time. And the reasoning can stop after 1 step or 1,000 steps. It can go on forever if the resources are there. So the bottom line there, the non-axiomatic reasoning process is a non-computational process implemented in a computer. And that means that in each step, it is, of course, implemented with some algorithm executing in constant time. So in each step, it's computational. But the system's problem solving of dealing with a problem, like the ones Patrick showed, they are dealt with in a non-computational way. The more time the system got in Patrick's example, the better it got, so to speak. But it could deliver an answer already after 1 instance. And also, as Patrick mentioned, this truth value of frequency and confidence can really handle both positive and negative evidence at the same time. And extremely importantly, NARS is not pre-trained as compared to all machine learning based systems. NARS learns in interaction with its environment. It has a fixed set of mechanisms that are applied in each cycle. So it learns, it's born, so to speak, with these mechanisms and learn after it's born. And one way to describe it is that as Patrick showed with the X and Y symbols, the meaning of a symbol is due to experience. It's an experience-grounded semantics rather than some objective meaning of X and Y or cat and dog, whatever. So it's neither typically what's described as computation nor a dynamical system. It's more something of a self-organizing process. So in a way, NARS is different from both symbolic AI and machine learning. So I will now show a bit more how we interact with NARS, and then say what I mean with machine psychology and demonstrate a few more of these experiments. But I suggest that we take a 5-minute coffee refillment break. And yeah, so let's have a 5-minute break.
No, I agree. Feels like real intelligence.
Yeah.
Let's continue. Let's continue. Okay. Now I can't hear myself. Great. So I will now give some examples of how we do this research from the perspective of learning psychology and relational frame theory with NARS. And one way to say it is that we, instead of an animal in an animal research experiment, we have NARS. So NARS is, so to speak, our organism in the experiment. So then the question becomes, how do we interact with this organism? And let's say, for example, that NARS was running on a robot like this. This is a robot that can pick colored objects and has for some reason been trained to put them in another place. And so this robot that's possible to buy, it has some kind of vision ability. And it has some kind of, let's call it location detection ability and color detection. So it could, for example, we have talked a lot about match to sample experiment. So maybe we could just, if we use this robot, for example, design this visual field as the middle being the sample. And as designers give arbitrary labels to other positions in the visual field. So left and right is just a label for a location, that the only thing is that it's different from right. And rel and func is just some other labels we use as part of our research. So this is one example of how we can encode a situation like this with NARS. And it looks a bit weird because it's really described as an interaction. So seeing something green to the left can be described as an interaction between seeing green and seeing something at the location left. So it's described as the top line. And the second line is an interaction between seeing something to the right and seeing something to the blue. Seeing a right location and seeing a blue color. And this colon dash colon sign is the way to say to NARS that this is an event in time. So this situation is described as two events in time. So it's possible also to describe a situation like this with multiple properties. Let's say that we have not only location detector, color detector, but also some kind of shape detector. We can then describe it like this, that the red triangle is described as two events perceived at the same time. So red triangle, blue square, green circle. So once again, it is a bit abstract, but it's a way of like describing how the system constructs its experience. But the important thing here is also, this is how we can use real sensors to reason on with NARS. And it started out as a hack in 2020 by Patrick and Tony, that they thought, maybe we could connect some kind of object classifier also to OpenNARS for applications. Let's say that we have YOLO, which is a very common object classifier. So maybe this is identified as a cat, a bird, and a dog. Then NARS can also reason on these events. So it can be like the eyes of the system can be an object detector as defined by some kind of deep learning model. Or maybe we have that in combination with color. So a red cat or a blue bird or a black dog. So what I want to stress here is that, okay, how do we interact with NARS? Well, using its sensors, and the sensors can be these deep learning trained models. So how do we then set up the system? So if we start up OpenNARS for applications or Aninal, these are the only things that needs to be entered. There's no like other pre-training, as I said. So this means that the system has one operation called select. It has two parameters, left and right. Volume is how much information we see. Motor babbling is that this operation will also, so to speak, when the system doesn't know what to do, it will with 90% probability babble one of the two parameters, left or right. So if we show this situation to NARS, it has no clue what to do. So we enter, for example, G exclamation mark, G meaning a goal. So we enter that as a goal event. And since the system doesn't know anything, it relies on motor babbling to, for example, doing the right, selecting right. So we can, as designers then, or the person interacting with NARS, present G as a consequence. And this is very important from a perspective of learning psychology, that the learning is an interaction. We are there interacting with NARS. I am the one who establishes G as a goal, something that the system desires. It's functionally equivalent to depriving the rat from water. If I haven't given the rat water for 10 hours, it would be much more eager to achieve the event of water. So it's that what G exclamation mark means. It's called an establishing operation. And it's we who present G as a consequence. We who deliver water, for example. But only from this interaction, the system learns that in the context of blue being to the right, and I press right, that leads to G. So the system observes this pattern. So only after one instance, this is a case of one-shot learning. The system learns this contingency. Let's say 100 time steps later, we show the same situation again with G exclamation mark. Now the system will not rely on motor babbling. It would rather use the knowledge it has acquired to select right. We typically don't use this, hand coding of NARSes. This is a way to connect NARS, OpenNARS for applications with its Python interface to a Python-based experimental framework here. And it's a way to really use the same experimental setup that we would use for a human being or an animal, but with NARS. So all examples I show now is conducted in this environment. Okay, but what do I mean with machine psychology then? It is a functional approach to the AGI problem. And I will say more what I mean with that. But it's really an interdisciplinary approach combining functional learning psychology with NARS. And remember that functional learning psychology was about studying the effects of regularities on behavior change. We can do the same thing with NARS. So we can manipulate the system's experience and observe the effects. But we have another possibility that is not possible with animals. We can also manipulate its mechanisms. We can choose which part of NARS is there, so to speak. So that's really what I mean with a functional approach, that we can isolate the effects of particular NARS mechanisms and that effect in combination with the system's experience. So that's really, so to speak, we can at the same time then change the system's experience and its mechanisms. So, and the thing we study is the system's behavior, the system's adaptation. So it seems like then that this setup of an interdisciplinary theory between learning psychology and NARS is the kind of setup where we could then use relational frame theory in combination with NARS to potentially have a very powerful AGI theory, a theory that is implementable in a computer system. So what have we done with this? Some short examples of operant conditioning. And to be perfectly clear, with operant conditioning, there's only two parts of the system that are needed. So reasoning on events and also reasoning on the system's own operations and goals. So these are described in Pei Wang's non-axiomatic logic as the 7th and 8th layer. But in Patrick and Tony's OpenR for application, one way to say it is that the system starts with this. This is the heart of the system. It's possible to compile the system with only this in as part of the system. These ideas that I talk about now is described in this recent paper published in Frontiers in Robotics and AI, where we talk about machine psychology, but also then this these experiments that I show now. So the three top lines there, semantic inference level, allow var intro, and functional equivalence. These are compile time parameters that you can enter in the config file of ONA before compiling it. And then when you start the system up, you write the things there with the stars. That's once again the only thing needed to start a system that then only has the abilities of temporal reasoning and procedural reasoning. So you could then have an experiment like this and use the experimental methods from learning psychology. That you, for example, have some kind of baseline training and testing, and in the baseline you you don't provide feedback, but in the training you provide feedback, and then in the testing you remove the feedback test if the system has learned anything. So let's say that the task is to select green independent of location. The system, of course, doesn't learn this during baseline because there's no feedback, but as soon as we give feedback, the system gets more and more correct. And in the testing, once again, without feedback, the system has learned this perfectly. And the green line is just another way to graph the results here, that the one part, I mentioned that NARS has a truth value that includes confidence and frequency and confidence. So the confidence in this hypothesis, for example, if left is green and I select left, that leads to G. The confidence of that hypothesis increases with training. And already with this very small NARS system, it's possible to study something like this task. Let's say that we have the same task. Learn to select green independent of location. But then in the middle of the task, we change the task to the opposite. Oh, now I instead give feedback when the system selects blue rather than green. So can the system first learn to pick green and then later learn to pick blue? So during baseline, it doesn't give any feedback. It learns the first contingency very easily in training part number 1 and demonstrates that in testing. Then in training part number 2, there is this retraining. So the frequency value of the green hypothesis goes down when it gets negative evidence, but instead the frequency value of the blue hypothesis go up. So to start with, the system learns the green hypothesis, but over time starts to instead act on the blue one as that get more feedback. So, and there's, as it's written here, it's 12 trials in every dot. So there's not that much of data for this system to quickly readapt. The conclusion from this is that only the mechanisms of temporal and procedural reasoning gives rise to operant conditioning. So as I said, that in a way, these two NARS mechanisms implement operant conditioning, implements this biological process. And I'm not an expert at all in reinforcement learning, but given my understanding already at this stage, this is quite hard for a reinforcement learning system to describe a utility function or whatever that can be something else in the middle of the task. But I think this task also exemplifies how we can use this procedural setup with a system like NARS, procedural setup from learning psychology. So next level of difficulty. So if we add what Pei Wang calls variable terms, the mechanisms of abstraction, we can get the generalized identity matching. And this is a paper we published on the 2022 year AGI conference. Once again, the system is set up in a similar way and is trained to, in the context of green, always pick green. In the context of blue, always pick blue. But can it then generalize to new colors without having been explicitly trained for that? So this is the same as the sea lion was doing. And it's possible to learn given that NARS, it is trained on green and blue, but given that it can introduce variables, it's possible with this abstraction mechanism, it's possible to learn a more abstract hypothesis that it can act on. So the results can be described like this, that the confidence value of the general hypothesis goes up even quicker, and that's what the system uses in the final test. So I think this also stresses how with only one additional mechanism we get much more advanced abilities in the system. And all the examples that Patrick showed, the comparative reasoning, in a way there's some other, let's call it, mechanisms involved, but on a complexity level is around this level. Something we have explored only during the last year is another type of complex learning called functional equivalence. And functional equivalence is something where we have used a part of what Pei-Wang calls reasoning on statements as terms. And this was published as a workshop paper on this the AGI conference that was in August. And so the compile parameters here are that we allow variable introduction, as in the generalized identity matching case. We also have a parameter called functional equivalence that enables this particular mechanism. And if we start up the system like this with two operations, operation 1 and 2, we can do something extremely simple like this, that if an event A is shown, the system carry out operation 1 that leads to G. So it learns the continuousy A operation 1 G. And then we have the event B and the same operation. Very important. It's the same operation, operation 1 in both of these examples. Then the question is, can the system derive something based on these? And the logic, so to speak, suggests that A should be functionally equivalent to B. They are now substitutable since the same operation, in both cases, the same operation led to G. So it's in a way the same, the role of a spoken word and a written word. They are totally different, but they can trigger the same behavior leading to the same consequence. And how we restricted the system to not explode with derivations was that when the system acted on these contingencies, the functional equivalence was derived. So to test this in an experiment, this is, by the way, what I like to do the most in life, so to speak, that I find an experiment in learning psychology and reproduce it with NARS. I can't describe enough how extremely rewarding and exciting it is. But here we had a paper published in 1997 where they had done an experiment on children who were age 4 to 5. And these children, they were trained on a particular task that these symbols up there, let's just call them X1, Y1 and so on. It was nonsense symbols. The symbol was placed in the middle and the child was trained to either put it there or there in the first run. In the top right corner or the bottom left corner. So for example, X1, when they put that in the middle, the child was trained to put that in the top right corner rather than the bottom left. So they trained that both A1 and B1, both these two, should be put in the top right corner. Both A1 and B1 should be put in the top right corner. And both A2 and B2 should be put in the bottom left corner. Then the question is there a functional equivalence derived between these symbols, because it's the same operation of putting it up in the right top corner or putting it in the bottom left corner? So here's how it can be described in a more abstract way. We trained with the symbol A1, we trained response 1. With symbol B1, we trained the same response, R1. So A1, R1, and B1, R1. And we also trained A2, R2, B2, R2. And then they retrained the children to do R3 and R4, which is to put it in other corners. There is quadrant 2. And test a generalization. So here is how it's described with NARS. So if with A1 and B1, we train the same response, R1, and with A2 and B2, we train the same response, R2. Can the system then do any derivations based on the relation between A1 and B1 and A2 and B2? We can test this by retraining A1 to do R3 and A2 to do R4. We then do this test. Will the system with B1 do R3 rather than R4? And can it with B2 do R4 rather than R3? And this is what's a typical thing that is enabled by this mechanism of functional equivalence that we implemented. We can encode it with NARS like this. We start up the system like this. It can, let's say that it motor babbles and with A1 tries out R2. This is, by the way, how we punish an event, that we write G as an event with frequency 0, confidence 0.9. 100 time steps later, we show the same situation again, G exclamation mark, the system babbles a new response, and we derive this contingency. So anyway, the system can learn in the retraining the first 4 of these stimulus-response relations. It's quick to do the retraining. And then during the testing, it's a demonstration of that it uses this derived functional equivalence. And the green line shows the functional equivalence between A1 and B1 and A2 and B2. So it's the confidence in that general hypothesis that increases over time. So this is, once again, it required one change to OpenNORS for applications. It's inspired by Pei Wang's NAL5, reasoning on statements as terms. It's a very good example of what Jan de Houwer called complex learning. He would probably call it, it's not an effect of meta-regularities, rather it's a joint impact of multiple standard regularities. So it's a very good example of how we used learning psychology as a theory to have ideas on what to change in NARS. And for the last 5 or 10 minutes of this talk, I will say something about arbitrarily applicable relational responding. And remember, this is this ability that is, can the system learn to relate? Relating is an operand. Can the system learn arbitrary relations that it can then use in various situations and derive from? You remember this symmetry example, for example. And this is an example of something that we haven't fully yet implemented with NARS. But we think that we have isolated the two necessary mechanisms that needs to be implemented in NARS. And it's something that Pei-Wang calls acquired relations and implications. And these two together is what we believe can be used to, from experience, learn to relate arbitrarily. And we think that this can actually lead to very, very advanced form of relational reasoning that I would argue is on adult human level AGI. Only by these two extra mechanisms. Already now, OpenR for applications can actually do the most basic form of arbitrarily applicable relational responding. It cheats a bit and sees it as a higher order functional equivalence, which in a way maps to the simplest form of AARR. So ONA can actually learn this, that if it is trained to pick Y1 in the context of X1, and afterwards also with feedback learns the reverse, that when Y1 is the sample, it learns to pick X1. Then, if it's trained to pick B1 in the context of A1, it can use the learned symmetry relation, this transformation of switching the top for the comparison. This pattern of switching can be learned by ONA on this level. So this means that if we trained in the context of X1, I pick Y1, then in the context of Y1, I pick X1. This can be trained with feedback. Then we show these close in time, so to speak, where it says trained symmetry. Then we train in the context of A1, I pick B1. Then the system, without feedback in the final phase there, says test BA. Without feedback, it can then derive that in the context of B1, I should pick A1. So it's a more abstract description. As I said, it's represented with NARS as a higher order functional equivalence. But as I said, we believe that with acquired relations and implications, much more advanced pattern of, let's call it, switching and transforming relations can be learned. And I hope you can see the potential power of this, that if these two mechanisms are implemented and that we are correct, then the system could potentially learn extremely many relations from experience throughout its lifetime. So the only thing we as programmers need to do, or AI researchers, is to implement the mechanisms, and with experience the system will learn intelligent behavior. Very briefly at the end, something about application domains. RFT, which, as you have detected, is a theory that I really like. It's not only a theory about human level intelligence or cognition. It is extremely rich theory when it comes to applications. And as some of you in the audience know, I'm a trained clinical psychologist, so I learned about this soon 20 years ago in the context of clinical psychology. So maybe some of you have heard about the form of psychotherapy called acceptance and commitment therapy, which is a form of psychotherapy based on relational frame theory. So what I'm trying to say is that with this theory, it's possible to both study on an experimental level, but also connect it to a lot of applications, like understanding clinical phenomena as examples of relational learning, for example. Someone with depression might hate themselves because the concept of self participates in a network of same and opposite to various symbols or whatever. Sounds a bit simplistic, but it's really, really possible to talk about clinical phenomena from the perspective of relational frame theory. Language learning, education, understanding a lot of racism and hate crimes or whatever is really possible with this theory. So the point here is that if we can have a computer system that do these processes, it should be applicable to all these domains. Let's say that we want to stimulate 10,000 instances of depression or want to try out new education methods, then maybe NARS can be part of that. And here at Digital Futures, we typically talk about these 4 application domains: smart society, digital industry, rich and healthy lives, educational transformation. And obviously, all of these can be targeted. So conclusion of this talk is that, as I said, AGI might very well be the most important invention of all time for the future. It has been called the holy grail of AI research. If it's implemented, it could for sure disrupt the entire society. Learning psychology and RFT, I would say, offers an extremely rich theoretical framework that gives a very, very nice perspective on general intelligence. NARS seems perfect for implementing the principles from relational frame theory and learning psychology. And as I said, it's functional learning principles rather than particular mechanisms. And it might sound a bit weird here, but it's not mechanisms in the traditional sense of associative networks or some kind of propositional network. It's more this self-organizing process of NARS that we can use to implement these, in a way, biological principles of operant conditioning, for example. So as you also have understood here, that we take an animal path towards AGI by really starting with the most basic experiments, which are still quite complex, operant conditioning, and building up from there. So machine psychology then is this interdisciplinary approach combining learning psychology and NARS, and becomes a very, what I would call, scientific approach to the problem of AGI. Scientific in the sense that we can manipulate independent variables both on the experience side and on the mechanism side and study the effect on adaptation. So I think a further benefit in this time when AGI highly likely happens within 5 years, there's a large value, I think, in having a cognitive model that so well fits to solving problems in society. Relational frame theory is that cognitive model. So I think it also shows how this type of work can have a massive influence on many important application domains. So with that, I stop there, and thank you very much for listening. So any questions from audience or Zoom audience, or?
I think there was somebody in the chat who had a question.
Great, thank you. Oh, no, great. You mentioned that the model is not pre-trained, but surely it's trained on some kind of language model to be able to produce an output solution to the task in English. Would it then not hold biases from the way it was trained to understand that language? I would actually say that it is not trained on some kind of language model. It's not trained on a language model. NARS has these mechanisms that I was speaking about: temporal reasoning, procedural reasoning, abstraction, functional equivalence, and potentially acquired relations and implications. There's no like language in them, but they can combine with experience to become the building blocks of learning language in a human way. Then, of course, when we do things, we put labels like left and right, but they are only labels for the system. Do you have any further comment on that, Tony?
I think sometimes people, they don't necessarily understand that when we run all these experiments, NARS doesn't have any knowledge. Every one of these experiments has been run from a completely blank slate. Everything it's acquired in terms of learned has only come from that experiment. There isn't any pre-training at all. There's nothing in there other than what it's learned from its experience. So any biases that are applied here are purely a consequence of its environment. And of course, there will always be biases from your environment, but isn't that really what you want, to be biased towards your environment?
Yeah, and I hope everybody hear what Tony was saying, that in a way NARS starts out really as a blank slate in the experience sense, but has a fixed set of mechanisms, and learns all of what we have shown here as part of its experience. And it can then be biased in the sense of what experience it gets. But two different systems with two different training histories get then biased in two different ways. So it's not biased in the same way as some kind of, I don't know, language model can be biased based on its training data. Yeah, Martin.
Yeah, I think I have a related question.
What question?
A related question to this.
Yeah.
So Patrick mentioned, or he showed some rules, which I don't remember what it was, but it was something, is an animal. Like the concept of animal applies to some other concepts. How would you get that from experience? Because you don't have like animal is like a super concept of other concepts.
Yeah, such a great question. So Martin is talking about in this very first slide, Patrick showed this.
Yes.
And it's such a great question because here in this slide, Patrick described the general non-axiomatic logic. And at layer 1, we have these inheritance statements. And with layer 2 it's possible to have this property-based encoding cat is meowing or Garfield is an instance of animal. But here's the strange thing. We haven't used that in the experiments I showed. And once again, I can't say enough how I appreciate that you asked the question, because it so much touched the issue of what we have been doing these years, that in a way, the logic starts at layer 1 and 2 with these kind of normal reasoning. It's almost like assuming that the system has some kind of language ability, it uses the same frame of reference as someone who would have a language ability. So we don't have that if we only start with temporal reasoning and procedural reasoning. But then it, of course, becomes a challenge of, so learning symmetry would be the little foundation of being able to relate things to each other. The representation of that might look a bit more complex, or quite a lot more complex than cat is an animal. But I would argue in that representation that we acquire at that level, that's, as I see it, exactly how it works for human beings. So
in this case, it would be like given to the model that the cat is an animal.
Yeah, exactly.
But I guess essentially we would like to learn that from some kind of data.
Yeah, it would be basically input by, it assumes that there's someone who inputs this to the system.
Yeah.
Of course, we can use YOLO terms again, maybe to describe this, but personally, I think that's a bit of cheating, at least from the perspective where I come from. Do you have a comment there, Tony?
Yeah, do you want to come near the mic?
Yeah.
I've got
Actually, the mic is all over
It's
the
all
place.
right, okay. So I've got a few things that relate to this. We have two phrases that we use to kind of capture this problem. The first one is,
You can stand here so you're in the camera.
there is no spoon, right? So all the fans of the Matrix movie will understand that there is no spoon. What does that mean? Well, it really means that perception is about a bunch of properties you detect, and the spoon appears as a conjunction of those properties, but it's not really a spoon. It's just a collection of properties that if we have another sound of it, for example, that says we've heard the word spoon, and we associate that sound of spoon with this collection of properties, and we create this connection. The other phrase I'm going to talk about is like, where does the cat come from, right? So we talk about a cat, but really these are just labels. They aren't grounded symbols. They don't mean that there's a cat. They just mean there's some association between cat and animal, which we have to learn. They could be X27 and Y28 as labels. So the real challenge here is how you ground these symbols. So for us, the idea of grounding the symbols is in behavior and perception. Everything is grounded in that way. So you form these relationships between what you perceive and what you do. And over time, you build up the idea of a representation of a cat in pure perception behavior. So it's a behavioral interpretation of everything we perceive. And in some cases, we acquire labels through language and sound that we attach to these patterns of perceptions and behaviors. But that's kind of how we see these ideas of these categories forming. So hopefully that answers the question to an extent.
Yeah.
Sorry, it's relatively very basic, I think, clarification question. So if this cat and animal are imputed, and I substitute animal with disgusting, then I'm forming the perception of a disgusting thing called cat. So I'm somehow injecting a biased perception. Say it's not a biased perception, but I'm forming the perception I want the system to have.
Yes, I mean that's true.
Dangerous, right?
I mean, yes and no. I mean, on the one hand, it's very convenient for us to be able to put the system in a state that we want it to be in from an experimental perspective. But on the other hand, I agree that you can bias a system in ways that you may not want it to have. But really, is it any different to a human being? You can educate people and bias them in all sorts of ways. So this isn't a solution to a foolproof system. It's going to behave like humans behave because it's grounded in the same basic mechanisms. So yes, it's going to be possible to educate a system in ways that we don't want, of course, but it's ultimately down to us as researchers and society to make sure we build these systems and educate them in a way that we want them to behave.
Yeah. What I mean is that somehow you are training the system. I'm not sure if it's called educational training, but
education is a good word.
Yeah, probably you are educating the system based on your system values, but it's not totally wrong to say that somehow the system is trained.
Yeah, but it's the same as how we train children, for example.
Yeah.
Of course, the values of the parents, for example, influence that training or education.
Yeah.
Or a teacher at school, so to speak. So NARS is similar. The way Pei Wang often talk about, if this is the path to AGI, there will be a lot of need for AGI schools, like arrangements where NARS systems with experience acquire a lot of knowledge as an equivalent to a school setting.
Yeah, I'm just thinking that you could potentially imagine educate a system according to a set of values, then educate the very same system according to the opposite set of values, and see how they are interacting potentially with the same environment.
Absolutely.
You would be in this position with this framework. Yeah.
And a short comment also on that, and I hope I don't confuse people too much here, but there is some nuances here also related to Martin's question, because if we take your example of, let's say that we want to train someone to use the term disgusting. Mm-hmm. So let's say that we want to train someone to thinking that cats are disgusting. Using this way of describing it, as it says on the screen there, it's perfectly fine with the null logic to describe it as cat has the property of being disgusting. And here's the thing that might sound confusing. We are actually removing that part of the system because how we think about properties is more what Tony said, that it's only about perception and action, perception and behavior. So what does it mean in behavioral language that something is disgusting? Well, I might have some, let's call it, perceptive event and notice some kind of body reaction. Or I might choose an action of avoidance, for example, in the context of something being disgusting. And what I'm trying to say is that it becomes a bit different when we use these contingencies, as I call them, like precondition, operation, consequence. We can use those temporal statements to describe that the cat is disgusting. That's a bit different from describing it like that. But personally, I think that that's a much more interesting path of describing meaning with language in that procedural, behavioral way. A lot of people have reactions to that. Oh my God, that sounds too behavioristic. But personally, I think that's a very, very valuable path that I think is I think it's very compatible with our path to AGI.
Yeah, so you said that you've identified two mechanisms from the non-axiomatic logic that needs to be implemented into the ONA in order to to get to this AARR. And then I wonder, okay, let's say you manage to do that, and the system can do this AARR. The system has this AARR faculty. And then it sort of goes from an animal level and takes this one of these last steps towards kind of a human level intelligence, in that it can do this relational framing and really have these vast network of relational frames. Then I wonder, what is sort of the constraint in reaching a real adult human level intelligence in terms of like memory and compute? Have you thought about that? Obviously, I think you have, but what do you think about that? I would think that the network of these relational frames between concepts would have to be fairly large. So what do you think about that? Would you need a super computer in order to simulate one human adult level AGI, for example?
So very good question, and I hope Henrik could be heard to the online audience. His question is really about, okay, let's say that we have the last two mechanisms, acquired relations and implication, in place. What would be required to have all of these typical human level cognitive abilities in place? And I give a first shot at the answer. And so I now take on my behaviorist hat again. And we as behaviorists, we don't talk about memory. We talk about remembering. So remembering as an operand, that means that you know how it is yourself, that remembering is so influenced by the current situation and your experience and whatever emotions were there, so to speak. And another, let's call it behavioral position, is that everything happens in the now, and remembering is an act of construction, so to speak, in the now. So already now, Ona can remember in this sense, but when we have the ability to derive as part of the remembering, it will of course be much more advanced. I can't personally say if there needs to be any change to the, let's say, size of the Ona memory or something like that. We deal with insufficient knowledge and resources, so it needs to be bounded. And the tough task is not then to remember a lot of like infinite, amount of events. It's really to have compressed representations and for example, that participate in these frames that you mentioned. With that said, there's of course a lot of architectural work that needs to be done. I point to Tony because he's our architectural expert in the team and think a lot about this. So maybe you have some comments on that.
So I'll come at it from the perspective of a computer scientist as opposed to the psychological perspective. And it's a reasonable question, and it's one we struggle with all the time. Like, how much processing power do we need? How much memory do we need? But actually, I think it's kind of the wrong question in a sense, because we're not really building a human being in the same sense. We're building a capability of thinking like a human being. So there's probably a relatively finite set of relations that you need to learn from the environment. And given a finite set of relations, you can actually use those to derive really complex things, but you don't have to remember everything. You can do it on the fly. This whole process of relating in real time lets you work out the connection between things in a very adaptive way. So you need a certain level of capability. But the nice thing is that even a relatively small system would have the ability to work on fairly complex problems, but it couldn't necessarily remember everything. But you can just plug it into Wikipedia as a form of memory, and it can just extract facts once it knows how to interpret the information.
Yeah.
So it's quite an exciting idea in the sense that you don't really need these massive human brain-sized systems.
Right. I would think that when you have the system sort of go to school, that's what I'm looking at. I'm asking about. I think, like for example, what we see on the screen here, a cat is an animal, and Garfield is a cat. I mean, the size of that sort of school that you have to train it with, is it? Could it be in a laptop, or I mean, how large is it?
I will answer really naively because if you didn't detect it, Patrick's demonstration of Animal, one feature of it is that he removed some dependencies, so he compiled it to WebAssembly.
Yeah.
So the AGI system runs in the browser. So personally, I expect adult human level AGI to be able to run in the browser. So that's the end of my naive description.
Yeah, and it can run on a phone. It just depends on how it connects to information, because we use a lot of information stored in our heads, and we kind of rely on that. We don't have ability to connect to the internet, but you can imagine that an extension of a system's knowledge and its environment could be at the speed of light. It makes a big difference to how big something has to be if you can find the information you need all the time very rapidly. So I think I kind of believe that a good-sized desktop computer will be more than enough to do something very effective. Yeah. But until we've done it, we're not going to know.
So I will stop since the event has officially stopped at 6 p.m. I will stop the recording now, and everybody is free to hang around. But thanks everybody online for watching. Thanks to the audience here.
Yeah.